Okay, so lecture is starting. Please clear up your desk. So, any questions about last time? So we did the linear. We did the first separation variables in linear as a special case, a linear differential equations. Any questions about it? So there is an extra part here at the end, which is optional at that section. So moving on to the next section, change of variables in ordinary differential equations. Okay, so it is very typical to do it in mathematics. And outside of the idea comes from outside of mathematics, because if we change units from seconds to minutes, or meters to feet, or pounds to kilograms, the result should be the same, basically. Okay, and then and you should be able to transfer from one to the other. So it is a requirement. Okay, and whether you do the simplest change of variables, change of units, and the second one is the change of frame of reference. As you can see, it's a big deal what you put in the center, the Earth in the center of the universe, or the sun is at the center of the universe. So the mathematics is very different, and that's if we have time, to show that, yeah. So if you rotation of planets around the sun is fairly easy to track. And meantime, if you think that actually planets rotate, imagine that planets are rotating around the Earth. Okay, then they trace such complicated trajectories, orbits. So they're not really orbits, just trajectories. And then so it's hard to explain them in some particular way. So the sun is very clearly going in a kind of it's a repetitive motion. Anything beyond that is the rest of the solar system is not working as easily. So let's change the frame of reference. Okay, so which is much more profound. It's also more of a tool than a requirement. So changing from seconds to minutes may be just a requirement of your analysis, that it should be you just basic physics or anything else. You should be able to translate from one to the other. It is a requirement coming from outside to mathematics. And here we might actually examine what if we do not understand something, we might change the frame of reference, for example, in order to maybe things look simpler. And it turns out that they do. So it's not that the sun rotates around the Earth, but rather the Earth rotates around the sun in that sense. And then the rest of the planets are just like the Earth. Okay, so they all subject to the same pattern, right? So it's not just the who rotates around whom between sun and Earth. Let's be clear, that's not the issue. The issue is, what about the rest of the planets? And so the answer is, the Earth special? Okay, so if it's not, then that's what turned out to be the case, is that the planets, just like the Earth, rotate in relation to the Earth to the sun, is the same as the planets to the sun. Okay, so that's the big idea, the Copernican system. Okay, which is you're all familiar with. Okay, so we are taking mathematically, it's not complicated, especially in dimension 1. And we're doing dimension 1. So change of units, you scale the graph, okay, in the either vertical or horizontal direction, depending on which of the two variables you change. And then frame of reference, the same once again, either horizontal or vertical shift. Okay, so you've seen this in calculus, pre-calculus. Sounds familiar? Shifts. So what happens with the function is indeed the change of one of the two variables. So here, what I'm doing here is I'm writing an original dependence of, say, space on time. Y depends on x, and then you might rescale either time, number 1, change of variables, number 2, change of variables on the output of the space. Okay, so these are the two cases for us to consider separately. And then units change is the simplest one, but it doesn't have to be as simple. Generally speaking, substitution is available. And then they always think of compositions. Once you see arrows following each other, you know what this is. It's the composition of function. So your function now, the original, which is in the middle. Okay, so it is now combined with so that's my function, and then it could be combined either the independent variable is changed or the dependent variable is changed, and then you need to have a new function. Okay, when the substitution is simple, then the relation to the original function is also simple. Okay, so starting with the case one. Okay, case one, we change the variable, which is the input variable, and that's the so the x-axis then is changing. So the original function is there in orange. Okay, is the x is the x and y, but then possibly we are transferring to a new variable, maybe different units for the time. Okay, so and then there was an x, and now I also have t, and then as you can see, those arrows at the bottom, they indicate the change of the relation between two x's. Okay, so multiplication by 60, for example, if I were to go from minutes to seconds, right, then it would be multiplication by 60. Right. Okay, so so the end result is if so if we were to preserve the x-axis accordingly, then the end result is shrinking of the horizontal axis. So it is not really a necessary step. It's just a visualization of what you've done, because ultimately the axes do not have to be related to each other. So it is, you can just say, well, I relabel. So relabel and relabel, and otherwise it looks exactly the same. So you don't have to change the graph. Okay, just different labels on the x-axis, and that's the change of variables on the x. Okay, so it's not very simple, and fortunately we have something familiar from before: change of variables in integration, but also known as integration by substitution, which is by its nature is change of variables. Okay, so integration by substitution, because it is literally substitution. So you express one variable in terms of the other. In this case, I'm expressing. Look at it. This is the relation between the two variables. So I take this x, it happens in this particular case, it appears that x is equal to t, and then you substitute. Where you substitute into f, and then you have f of 2t. That's your u, the y. So it was used to be y equal f of x, and now we have y equal 2t in this particular case, or in general, it is f of g of t. Okay, so that's the composition, that's the substitution. The same story happens with integration, except, so it's, remember that integration is the simplest ODE is an integral. Okay, so it is what's the ODE? What's the ODE that corresponds to this integral? Before we actually evaluate it, what's the ODE? The derivative of something is equal to something else. What is?
dx is equal to 1 over x times e to the x squared.
Okay, so what's the right hand side? This is the right hand side. What's the right hand side again?
1 over x.
Well, where is 1 over? Where did 1 over come from?
Because you have to take it to the other side to make it an equation.
No. It's a. Remember, what we're looking for. This is, I put f uppercase here. This is an antiderivative, and it is what we're looking for, right? Evaluating the integral is you have a function. This is here, and you find its antiderivative f. So this is maybe f lowercase, and this is f uppercase, right? So from f that is known, we have to get to f uppercase. Okay, that's the integration. That's calculus 1. Okay, indefinite integration, finding any derivative or integral, in other words, indefinite integral of the known function. Differential equation goes the other way based on the fundamental theorem of calculus. So what's the function? What's the equation? This is the antiderivative. Why is it called antiderivative anyway? What? So that function we're looking for is an antiderivative of ex squared. Okay. So what's another way to express the relation? Antiderivative, why is it called an antiderivative?
Because it's the inverse of derivative.
Well, the inverse of the operation, derivative is an operation goes this way and derivative goes that way. Okay, so as you can see we're here going for and from antiderivative from f, that function, to f uppercase, and now we're going backwards. So f, as simple as that. Okay, so these two statements are identical. So how do we find the step instead of an equation? We can write it in one single line and just do computations and find what that f uppercase is. But and so that's the way the calculus 1 point of view is this, and this is ODE point of view. Okay, so what I'm trying to do here is just to look at the problem that is familiar from calculus 1 and 2. And then and solve it in a new way. Okay, so we know roughly what's supposed to happen. I hope you remember how we integrate by substitution, and then roughly we know what to do it, and then that idea will be then pushed forward to general ODEs beyond the simplest case. Okay, so this is how it works out. Just to refresh your memory, we recognize the presence of a composition in this expression. So where's the composition?
Like squared.
What?
X squared.
Well, composed with what? The first step is x squared, the second step.
X.
What?
Over.
The exponential function, right?
Yeah.
So that's the composition. Usually you have parentheses to see composition. In this case, they just align in such a way that maybe it's hard to see, but if you go from x to x squared to exponential functions. Okay, that's consecutive computations. It's a composition. Okay, so that's what it is. From x to u. Okay, so u is computed by x squared, and then right like this, and then that u is the input of the next function in the composition, and it is e to the u. Okay. So we decompose, that's literally what it's called. So that function ex squared, we ignore x, that coefficient x here, so ex squared is decomposed because you can see why, because u will be our new variable. We're gonna translate this integral, the original integral, into the language of a still integral, but with respect to the new variable u. Okay, with hopes that it's gonna get simplified. Okay, remember this. Okay, so just to mention that calculus 1 and 2, just about everything that has come up in calculus 1 and 2 will appear in this course, unfortunately. So, all right, so okay, so then we did this. We also already did extra work in this direction. We actually explained the integration by substitution by means of the differential forms. Why do we need differential form for this one? Once again, as I told you, we want to translate this integral to the integral with respect to the new variable. That variable has been chosen to be u. Okay, that can be new variable, but it would be very easy to translate. Hopefully, x's into u's. We have a transition formula: u is equal to x squared. So that's what we are going to be using. But what about the dx? Dx will not automatically be translated, so it have to be computed, and dx has to be expressed in terms of dx in terms of du and u. Okay, so that way we'll be ready to carry out the substitution. So because it's an integral, so it's not just the function itself that needs to be recast, which is going to be easy, but rather also the rest of the integral, which is dx. So we do it with differential form. So we compute du from x squared is equal to u. We differentiate, and that's what the differential form is. The differential of u du is equal to x dx, and that's exactly what this is the dx that we care about. So dx is this dx. Okay, so dx in the differential form that we integrate is is now found almost, but certainly we are going in the right direction. So translation takes, like I said, there are two levels of translation. X is with use on one hand, and then the X is with use. Okay, so two level translation of our integral into with respect to X into the one with respect to U. Okay, so then I could just solve for dx and substitute that. Okay, so once that equation, x ex squared dx. Okay, so we know each x will be replaced with square root of u, roughly speaking, and then what's left, it will be the dx will be du over 2x. It works out quite well. So as you can see, as I take my integral over here, I split it into two. One entirely depends on x, the other one entirely depends on dx. And then I substitute. So I actually do not do it. I keep this because I'm not doing this. I don't really. It turns out to be I don't need it. And then and so x, and then this one is carried out. Dx comes from over here, and it is du over 2x. X disappears, cancels out. This key x cancels out. I end up with 1/2 du du. Okay. So that's the change of variables in the change of variables itself has nothing to do with integrals or derivatives or calculus. It's a pure kind of a function. So just to substitute one into the other, that's all there is. But in calculus, when we speak of change of variables, we also speak of change of variables of the derivatives, or in this case, differentials. And so we need to know what to do, which is do not just replace dx with du. They're not the same. How are they related to each other? That's how. Okay, so if you just do it carefully, do not presume that that's what happens. It isn't literally multiplication. That's the once you start looking at the integrand of as one whole expression, not just what I circled there, but the whole thing. Then you know that how to deal with it. You are doing it more carefully here. Okay, so all right. So any questions about this change of variables? So original this, final that. Okay, so what we here is we see here is the change of variables complete. So there are no x, there are only x's on the left, they are only u's on the right. Okay, and the integral is simpler. Okay, so that's the big deal, because that's the point. From the top of your head, you might not guess what the answer is, but that's the point is simplification. So that is the point. The point is how to simplify, and that's where we are with our differential equation. That the certain we're going to see an example. The certain circumstances, your change of variables will turn an unfamiliar, maybe complex differential equation into a simple one.
So whenever we finish it, we leave it in terms of u.
No.
Or we switch it
No,
back?
so you carry out the integration and then you do back substitution. So the problem is, so your answer should be in terms of the original. Your answer should be in terms of the original question, right? So there was no u, you made it up. So this one is made up by you. So the question is then posed by somebody from elsewhere. So they haven't seen that u. So that keep that in mind. And so sometimes they call it u substitution, and then everybody uses u, and then you might assume that u is the final goal, but it's not. Okay. So then you have to do back substitution. So integrate, then back substitution, and then you're done. Unless, of course, it's the integral is definite, right? If it is a definite integral, then you can avoid back substitution, in which case you have to deal with the, change of variables for the upper and lower limits of the integral. And so that we're not going to be doing that. We will be pursuing this plan. So actual integration, or in our case, we will be solving the simplified differential equation, and then back substitution will give us the answer. Okay, so that's the integral. So far in the integral, and so the tools that we use with enhanced by using differential forms. I think it's not that differential forms make your life easier. They just make your life harder in the sense that but better, because you're not less likely to make that mistake and just replace dx with du. We know what dx is. It's a number, and dx is not the same as the number du, and so they have to be linked to each other in this particular case when we do compute these the differential form in this manner. Okay, all right. So the good thing to try to refresh your memory about calculus 1 and calculus 2. The substitution is sometimes hard, sometimes it's easy, but if a substitution is given to you, you should be able to actually finish the integral without guessing, because it is the hard part is to come up with the substitution. Sometimes it's entirely not obvious. So we're not dealing with that here. So we know what the substitution is supposed to be. And then after that, everything is automatic. So ingenuity, insight might be required to find what the exact substitution to choose. But once it's chosen, the thing goes automatic, including the part that maybe if your choice it was incorrect, unwise, let's say, you can still finish the substitution. So if you choose y equal x cubed in the above integral, it is not going to simplify things, but you can still should be able to finish the substitution. That's how you will know that it doesn't work. Okay, so you do substitution, trial and error. You finish it, you realize that the integral that you end up with is not simpler than the original. Okay, in that case, you know that your trial failed, even though you did everything correctly. Then your premise that your substitution makes sense will make things better didn't work out. But everything else was correct. So it can happen, it does happen, and so keep that in mind. Okay. So let's take that computation here and translate it, as I suggested right here, into the language of differential equations or differential equations. So here it is. Okay, so just once again, gradually moving in the direction from simple to more complex. So this is my differential equation, as I promised. Okay, so it's very simple because why it's simple? Because there are no y's on the right. Okay, so. But we're not doing an integral right now. Let's just convert literally and produce, rather than making one integral from the original one. Now we're making new derivative from the original. Okay, so once again, switching to Leibniz notation is very productive here because it's once again reminds you that it's not just literal prime. Here it is actually there. These are the numbers, and then you can manipulate differential forms. So dy dx is equal to x ex squared. Same thing. New variables already has been decided will be x squared, okay? And once again, the clue to you, if there is a substitution or composition, that will be a new variable, okay? We have three variables to worry about now as the unknown function, y in terms of x. Once again, I did not name the function. I used the name of the variable, the output variable y for it, okay? It's still to be found, no matter even if the kind of a circular function. And then we have a new variable u is equal to x squared, and then the unknown function is now the other unknown function with the function with the same name. It might appear y depends on x on one hand directly, and then y depends on u as well. And so these two are different functions, obviously. So I don't want to name that these three functions. We have three of them, but they produce the same result. So from x to u, that is known, the u equal x squared. Then from u to y, it is this original unknown from x to y. Okay, and then the hope is if we shift from this diagonal line to this vertical line, the new unknown u depends on y will be simpler. We know that it will be, and we just have to execute it. Okay, so once again, differential equation that this one with respect to x. And then we want to it with respect to u. That's the idea, but it's still just a differential equation, just like we replaced one integral with another. Okay, so all right, so let's just prepare things. So we have three variables. So let's look at the differentiation. So once again, from x to y, this is my differential equation. So that's the original. Okay, now I'm looking at we decompose it according to our plan. So I go from x to u, from u to y. Two functions or two dependencies rather, and they both have derivatives. Naturally, u equal x squared, the derivative is equal to 2x, so that's it, that's all there is. And this one is actually where we don't know. Okay, so known, unknown. And then what's the relation between those three quantities or three functions? CR stands for yes, the chain rule, correct. The chain rule indeed. So the relation between the variables is through this. Let me put a circle here. So this is about composition, right? So from x to u, then from u to y, it's as if you go diagonally from x to y. The chain rule works differently. It's a multiplication. So you have two derivatives. And when you multiply them, these two derivatives, 1 and 2, if we multiply them, that's the simple multiplication here, then you will produce dy dx. Okay, so it must, yeah, the chain rule right here. du dx times dy du is equal to dy dx. You can see the cancellation. Okay, so that's the relation between what we have and what we want. And so once again, we something that is still unknown, but we're not looking for it. We just want to translate our differential equation to the new language of use. Okay, so that's what happens. So that's the old differential equation. Okay, so dy dx is this. I just substitute right here. So I have three variables. I have cancellation of no, I do not. No, there's no cancellation. That would be pointless. But rather, what I do is I substitute. I know one of them. U dx is known, so this will be here. It goes. It is actually 2x. Okay, and then I do have almost my differential equation because with respect to u, because x cancels out. That us being lucky, or it is by design, this x cancels out, right? So, same way, the algebra is kind of the same as with the integral, just looks without all integral signs for us to worry about. So 2x dy dx is equal to x eu, okay? And then the substitution, as you can see, the substitution has happened right here. And then I cancel out x and bring 2 to the right hand side, and I have a new equation with respect to u only. And it is simpler. So once again, we will make observation. This is pretty much identical to the ones about the integral. The change of variable is complete, and the new problem is simpler than the original. Okay. So it's entirely a substitution, so that part is over. The simpler differential equation, either we simplify and maybe we might need to simplify again, or in this case, we already know what to do it, and you can tell me how do we solve this differential equation. Let's do that again. No, I don't want to go back. I solve and then I go back to substitution. I have to solve it first. Well, the answer is already discussed. There is no y on the right. That's what makes it's in, so no y here. So that's what makes it elementary. When there is no y on the right. So how do we solve a differential equation with no dependent variable present on the right? Solve it.
Multiply both sides by du and integrate.
Well, yeah, yeah. So in other words, the key word is integrate. You integrate on the left or on the right, either way, cancellation on the left, and on the right you have your exponential function. So you have one half eu plus c, and that's the answer. The answer with respect to u, this is the next step. The back substitution has to be carried out, and this is the answer, the final answer, plus c. So again, so in integrals, in integration, you know that plus c to add them as a ritual. Now we know that we actually more just be careful about and it's an equation now. In integration, you might be wondering why it is plus c, but in differential equation, you shouldn't be wondering because you know it's an equation. So to solve an equation, we're supposed to find all possible answers. That's what plus c gives us. It gives all the solutions. So it's not one, it's infinitely many solutions at once on the right. So that's the meaning of plus c. Everyone with plus c, and no matter what c is, it is a solution of our differential equation, firstly, and secondly, there are no others. So this is the complete solution. This is the solution set. You can put it like this. Oops. C real. So this is the solution set. Okay. Okay, so any questions about this?
Well, I have one.
Yeah.
Up top, we go from, I don't know, it's just me, it's how we're computing it. You're going from du, dy, dx, and then. Is
Over
that
here?
just,
Over here?
yeah, but then you go over and it's dy, du.
dy du doesn't go anywhere, right? It's still there. right? As we're talking about this part, the dy dx are states, right? And then I will replace du dx. Right? From over here, the du dx it was computed by, so it's like our,
Okay, I see now. You're just moving it over and substituting.
right, right. So I do two substitutions, right? So I did this substitution and then that substitution. So these two come in. So this one comes in here and that one comes in here. Okay. And so, and every time it will work out exactly the same way. So dy dx, we don't do it, dy rather, sorry. Is we're not doing with it anything because we don't know what it is. It is in fact what we're after. So we certainly keeping it. Then the derivative of the substitution function, that's x squared here, is computed. And so it's used because it's known. And then what's on the right is just to have you have to complete the substitution one way or another. So cancellation, we were just lucky. And so x on the left and on the right has disappeared. Otherwise, we would have to replace each x with what square root of u. Okay, so that's, we didn't have to do it, but generally speaking, we might have to. Okay, so because the cancellation of x on the left and on the right, we didn't have to do it. Okay, so all right. So once again, you can same stories with integral. Your substitution may be unwise, and it will not simplify things. So be prepared for it. Make a mistake. So so if nonetheless correct or not, the substitution is, if you are supplied with the substitution, you should be able to carry it out all the way through. So that part is which is, let's say, so maybe not right now, but it is routine. It is just a recast integration by substitution. That's what we are doing here. Slightly more complicated way, but the reason, as I explained it, is because we're moving on to more complex differential equations, and so we're doing it the right way. So that was the independent variable. So that's we're inserting it into the original function. Okay, so but also you can try change the dependent variable, especially in the autonomous. This was a non-autonomous differential equation, but supposedly there is a y on the right and there is nothing on, there's y on the right and there is no t or x. Okay, so first of all, remember that's what it does. We are redoing the function that we, by the way, don't know what it is, but the substitution is with the y-axis. Once again, arrows go out. And the end result, if you interpret your change of variables of the y from y to c as a stretch, then what happens? The whole plane stretches in the vertical direction. So that's what has happened. But once again, you can also say that we just relabeled. We relabeled the x's. So it was labeled with y's, and now it's relabeled with c's, and that it doesn't matter. Mathematically speaking, there is no particular choice of the unit for the vertical horizontal axis. So that's a stretch. So that's a so typical substitution that comes up first. But really, let's look at even simpler substitution. That's a shift. Okay, so then if I do a shift on the vertical axis, location, I choose location to be 0 here, and then I decide to be there. Nothing else changes. So then what it does do to the graph, it is not changing its shape, it's just shifting in the vertical direction. And then so let's look at an example where it comes up in a very natural, predictable way. So in population with migration, okay, we have had the population model before, which is right here, as you can see here. So the change of the population is proportional m to the population as well as the period of time. Okay. Okay, so m could be positive, negative, depending on producing either population growth or population decay. We know that, but let's forget of it nonetheless, because what if there is an influx of people that are not born or that die? So some of these people are dying, some of them are being born. So from the outside, people coming in or people who are living here and then they're leaving. Okay, so that would be a problem that has changes our word verbal. Remember the beginning of the class, verbal descriptions of models then to be translated into into the language of differential equations, and so we already did, but now we complicate them, and that's the common theme is make model match the reality better and better. Okay, so where you see a city that actually does not have any inflow outflow of the population, no, so then they have to have might want add migration. Okay, and so see if what it does, how it changes the outcome, because we know what this produces. Remember, just to refresh your memory, we could have exponential growth or we have exponential decay. That's the normal behavior of the population. So, okay, so what if the migration? So once again, the simplest case of migration, it is constant. So per unit of time, there's same amount of population going in. Okay, so you can try to guess before you examine what the effect will be on the dynamics. So it's both the influx, positive migration into your country or your city. So how would that change the population dynamics?
Every so many people, you get an additional, however many.
The additional what?
So you just get the additional on top of what you already are.
Yeah, so in other words, case one, exponential growth, what's the result of the influx of population? What does it lead to? Faster growth. So at least it will be exponential, maybe faster. We cannot tell. So that's something to be resolved. Will it be still exponential, or there are functions that are faster than exponential, so, or maybe it's exponential, but with a higher rate. So you have like EX or E2X or just EX squared. These are the three possibilities of growth: exponential, then exponential with faster rate, and then the or sub, what is called, the growth that is faster than exponential, the EX squared. Okay, so case two, however, is complicated. Then, if you have a decay of the population, you're going towards zero, and you start to influx the population towards a constant rate. Do you have any guesses of what the population would behave like?
Decay slower because you're still getting more, assuming your end's positive, you're still getting an influx of people from migration.
Yeah.
But it's still going down, so.
Yes, but the actually, it will be going down, but there is a subtle way of how. So we'll discover that. So I just want you to see that just looking at the model and description is kind of complete, but nonetheless, the conclusion that we can draw is still non-existent. We have to solve this differential equation, produce it, model it, and simply do simulation, and then hopefully things will reveal themselves. Right now, just based on the kind of eyeballing the model, we cannot, some questions cannot be answered. Yeah. Okay, so let's create a model. So there is an extra term proportional to the time increment. So I'm taking that model and adding an extra term. This is the extra term right here. E delta t. So because it is proportional to the length of time that we are taking, right? So if a constant rate of population means that per equal interval of time, you have equal population influx or outflux, it's still a possibility. So there are a total of 4 possibilities, as a matter of fact, right here. Okay, so a natural growth, natural decay, and then we have an migration and immigration, in or and out. So case one is actually, we consider this case one, right above there, case one, and then I consider case case two. Okay, but there are still case 3 and 4. Okay, so the outflux, so you have a population growth exponential, but then every time people are living the cities at a constant rate. Okay, so all of your 4 cases might produce different results, and so right now it's unclear what it is. But the model is there already. Look at it. So we're going to solve it without reference to M or B, so that we take care of all the 4 cases. Okay, so the different situations are on the left is original, on the right new one. And okay, so what is comparing these 2 differential equations? So what is that in the context of today's discussion, what is the point? In the context of today's discussion, if you have any, you can suggest any plan to pursue. What should we examine? What's today's topic? Change of variables. Okay. Do you see anything that you might want to consider? So that seems like a very close. Everything is the same except for B. Okay, so it might be just a shift. Okay, so that's if you start you think about change of variables, you can start think about them more specifically. Seems like just a shift. Is it? Is it even possible that there is nothing? The difference between the two situations is nothing but a vertical shift. That's interesting, right? So maybe all the guesses is really that exponential function will be simply shifted, or in that case, will be also shifted in the vertical direction. Okay, so maybe that's all there is. So if we can pull it off, and so let's see if we can pull it off. But before that, we actually to confirm that we're on the right track. Let's do simulation. Okay, so if I choose k equal to 2, b is equal to -1, so it is people moving out. Okay. So, and that's what it is. So natural growth is b is equal to 0, and natural growth without flux, b is less than 0 right here. So as you can see, the population, if there is no at a particular value of the population, the actually it's stable. Okay, so roughly speaking, everybody's bored. Imagine that situation. Everybody who is bored during the year actually leaves the city. Okay, so it works out, and then it continues on. So at the end of the year, you have as many people as in the beginning, and so then there is neither natural growth nor decay. So that turns out to be a kind of extreme possibility. While it only can happen if you have natural growth, nothing but that. It only happens exactly the same when your city is empty. Okay, this one is not empty, but you are carefully manipulate things so that once again natural growth of the population is exactly matched with the outflux of people out of the city. So it seems to be that's what the picture on the right suggests. Otherwise, this is the difference. The exponential growth on the left also matches exponential growth on the right. I'm doing modeling just as we did in the first week of classes. Is once again I have a function right here, so I type them into my spreadsheet. The red is up, blue is down. And as you can see, there is this where there's a change between positive in pink and the negative in blue. That's where there's that stable solution. It appears stable meaning constant solution. And so above that solution, above that particular line, everything is going up. Okay, so where is that line over here? This is the line, and everything above it will go up, and everything below it will go down. Okay, so it's possible to go down. We just don't know what the question is, what is that number? So there is this kind of a steady state situation. A particular choice of influx might, if you are into kind of trying to manipulate it into a constant population, you could hypothetically. So that's what the simulation suggests. But let's go on with the substitution. So these are the two differential equations. So I go straight, I did the modeling, I compared, I have an idea that maybe working out. Look at it, it does look like a shift. So I take this graph over here and shift it vertically, I'll get that graph over here. It looks very much so, it's not even growing faster, right? Look at it, it looks very much similar. So if you compare this part with that part, looks identical. Doesn't it? So maybe there is no change of the rate of growth, except for the possibility that actual population might go down at a certain rate. Okay, so just it's plausible. So I write the two differential equations side by side. I'm very careful, and since this is actually where we are, okay, and this is the idea is to convert the new towards old. So that's the new population with influx outflux, and this is the old population with no outflux or influx. Okay, so there is no B. So that's a certainly different city in a way, and so I want to compare them, and somehow the transition is more or less clear now, but the way to get there, we also know that because the relation between the variables. Okay, so that's the shift, and A is unknown. That's my change of variables, but the problem is the change of variable is unspecified. So because I do not know, I'm looking at the picture, I cannot tell what that number should be. This seems to be the shift. The shift, this is 0, and this is some number that is unknown. What is it equal to? So from the picture, you can try to guess it, but that's would be unproductive. That would be give you one single number altogether. But it's certainly worthwhile an experiment. So the substitution is clear. So I'm doing substitution with unspecified A. Where's my A? Okay, so A is still to be found. So vertical shift by A, positive or negative, I haven't decided yet. And then this is my substitution. That's my function. That's everything is around it. Will be on it. And then I carry that substitution. Okay. So I take my first differential equation. I plug in. I replace y with z plus a. Okay. So z plus a prime is equal to what is it? Which is z prime. I'm sorry. Which is z prime. That's a type. Okay. So z plus a prime is z prime. Okay, that's my left-hand side of my differential equation, this differential equation. And then the right-hand side is mi plus b. And so mi plus b is transferred to m. Y is equal to z plus a, and then plus b, and then I simplify. So that's the substitution is finished here, right? And now we're trying to simplify if it actually works out. And so mz m plus a, it turns out it does have the same form. Mz plus some coefficient that is in the way, right? So remember, this is what I want. And what I get is this, which looks more complicated. Okay, so I want to have mz, and I got mz plus some business. So any suggestions of how we proceed from this point? How do we get rid of the last term? Can't algebraically get rid of it, is what it is, but the term depends on A. That's our way out. So what do we do? We need to find A which would fill this term, and so we would get what we want. So what do we do? Then equal to 0, solve for A, exactly right. So this is it. So the substitution is finished, but we're not getting just yet the left term. Hold on, I think this may have. I think an 8 piece of this missing part. When I was inserting it, some part of the computation has been lost. It's yeah, so it's unfortunately okay. So I have to write it out. Fortunately, it's not too complicated. Get rid of the last term, set it equal to 0, and solve for A, because that's the shift that we don't know what it is. Okay, so what I have here is m a plus b over m is equal to 0. So which means that a plus b over m is equal to 0. M assumed not be equal to 0 because that's there is no growth or decay. Equal to 0, and so I conclude that A is equal to negative b over m. Okay, so these are the substitution that will solve our problem. So before we proceed, so this is what the summary is, that we did convert the old this is why, by the way, linear, and this is non-linear. Because of the extra term, that's what it's not linear. The one on the right, we know how to solve. We in fact know the answer. But let's still explain what is that we've got. So simplification is clear. We know how to solve. Let's set it aside for a moment, and then you can actually try to interpret what's the meaning of b over m. Remember, what b is the influx, and m is the proportion, is the growth coefficient of your population or decay for that matter. Okay, so as you can see, if you're okay, so if the example that we consider B is positive, we're moving no, hold on a second, B is people are moving out while M is positive, which means that there's it's a good city, so the natural population is good, but we want, for some reason, we want to actually people not to stay. So what do? We pick a population that would ensure that that it happens in that one particular setting. And so then the growth coefficients versus right there, the comparison of the rate of immigration, okay, B, versus the natural growth or decay coefficient here, okay. So any shift could be vertical or negative depending on which way of those four possibilities, B and M, each of have two signs, and so there are two possibilities whether A is positive or negative. So when B is negative, M is positive, then A is positive. So you're shifting up, and that's what the example we saw. The shift was positive in the vertical direction. So then it is over exponential, still exponential growth, right? But in a higher level. So it's not exponential function starts at 0. Okay, so it goes towards away from 0, and this one is shifted. So exponential growth that it starts from upper limit, which that upper shift is determined by the influx, or sorry, this is influx, yes, influx. So it's faster growth. Hold on a second. I don't think my case here is made properly. So if this is a positive, the growth is then in the still exponential growth, but in the positive direction. So, and it's not A positive, it's M positive. And A is positive too, so that's a positive shift, which means that B is negative. Hold on, why B is negative? So A is the shift of the solution. Okay, so and it is in the positive direction when that doesn't make sense. Hold on a second. So M and B, A and B should be related to each other, having the same sign, because B is whether in or out, while A should be also in or out. So this in particular, what happened here? I think it just shifted, and then that's how I lost a piece. Yeah. It shifted. See, the whole thing shifted, and that's why. Okay, so I don't know. So it's pretty much lost here. Right. So B on the left, B and B on the left is what we're pursuing here. So I think I'm myself confused myself here. So we actually it's the same behavior, only shifted in the direction, and whatever the direction is. So we're not trying to manipulate anything. We just have in this particular case we have a natural growth without flux, and as you can see, the end result is still a population growth, but at a higher level. Why is it higher level? It is a typo here. Okay, let's examine if it makes any sense whatsoever. Okay, so the natural growth on the left. Okay. Okay, I see the problem. So yeah, so it depends on which way you go. You go from the left to the right, or right to the left, and then it's either positive or negative. Okay, so it's better to be done, and we have to look at this part and just to realize that it's not the same, and the variables are different. Okay, so the variable with respect to y and the variable with respect to z, they're not to be confused. And as you can see, the variable of here is we are adding a. That's where the positive shift happens, even though b is negative. Okay, so this is a positive. If a is positive, then this is up, shift up, and indeed it is the produces the the exponential growth on a higher level of growth. Okay, so let's just stop speculating. Let's just write up the answer, and we'll see what happens. In addition to the simulation that we have here, we also have explicit solutions, which is a miracle. And so, as you can see, I solved my new equation, just like with that integral. We solve it with respect to z. Z is bound. Okay, so z is proportional to itself. It's as if it doesn't really matter that this is some population, presents population dynamics in some city that doesn't exist. It is entirely a made up situation. And so when we have the realities on the left, on the right is just a modified differential equation, and we have a solution. Okay, but then that's not the final solution. We still back to do some back substitution, and so this is the end result. I replace y with z with y minus a, and then this is my solution, as you can see, and with a being negative b over m, this is my new solution. Okay, so let's examine and confirm that it makes every sense in the world. So B once again reflects the influx outflux. M is the natural population growth or decay. And then so for example, if B, well, there I have a picture here, right here. Okay, so M is less than 0. Okay, so M is less than 0, meaning that we have a decay no matter what. Okay, so population going in will not will produce growth. When look at it, the reality is split into two. So the reality is split into two. This is not 0 anymore. So so then both the growth and decay are possible. Okay, in this new model, when influx outflux is allowed, then you have both the possibilities. Look, they're very different. Naturally, here one situation, here is another situation. They are entirely different, even though. Look at it, M is less than 0, which means that it is a city that is dying, sort of. Okay, so then look at it. If you allow two people to either move in or move out, it then doesn't really matter. Long term, there is a convergence, right? Convergence, except without the population, the convergence would have been towards 0, and this is convergence towards something else. Okay, so if this number happens to be, this is negative b over 2m over m. Okay, so when this number is positive, hypothetically, if it's positive, then there are two possibilities. If the population is above it, it decays towards it. If it's below, it grows, but also in a decaying manner towards it. Okay, so there is a stabilization of the behavior. So if before we had only one possibility, what was above, it's always decay. So the city is dying, and dying in the literal sense towards 0. If people are moving in, then it is not dying. It is dying towards a constant value, which is not 0 necessarily. Okay, so that's what influx allows you to get. You'll not turn, if the city is bad still, because there are more people dying than being born. And so so the population then can be sustained in a higher level, but it will never grow exponentially. Okay, because once again, what determines the behavior long term is this birth rate versus death rate. And so if there are more people dying than being born, then you don't have any chance for this behavior, which is on the right. Okay, so so then the nature of the behavior is it does change. It doesn't have to die out entirely, but it dies out towards a constant population, if you like. This is the constant population. Okay, that's the dynamics, either from above or from below. So you can still either decay if your population was so high that your influx does not affect the fact that it will continue to decline, but it won't decline towards 0. On the other hand, if the population was small, but the influx is big, then there will be growth, but it will never grow exponentially. Okay, so that's the dynamics that we have discovered. On the other hand, if the city is healthy, so this one is healthy in terms of birth and death and so on, then what has happened is that either you have still exponential growth, but it does not start from 0, but rather from higher level, and then but it's still there's a possibility. That's the last one, case number 4, or I think it's case number 4, decline. Which does not seem realistic, but it is. What is it? It's like, hold on, where is 0? Let me make it realistic. This is 0. Oh, let me make it lower slightly like this. So if this is 0, okay, so then everything below 0 is impossible, because you cannot have negative population. Then you have always population growth, but it does not start slow anymore. It doesn't have to start slow and then accelerate. It already has accelerated from the beginning. So that's the difference that we have when you have an influx of population. So these are words, really. So a way to interpret the mathematics that we have established beyond any doubt. Okay, so whether or not the end result is a realistic model of anything, but it surely is a better model than the ones that does not take into account influx and outflux of people. So as you can see, we did answer the question about the possible dynamics, and they didn't really change that dramatically. It's still either exponential growth or exponential decay. And you might even ask, well, what's we've seen this picture before, not related to population. Remember what this is? What was the model of? Convergence towards something, nothing to do with population. The first day of classes, the first week of classes. Temperature towards, they converge towards the room temperature. In this case, we don't know what the room temperature is, and so that's the challenge. So to find what that room temperature is supposed to be, but then if it's too cold, then it goes up. It's too hot, it's going down. Okay, so but the point, of course, of this was just an example, not solve this particular problem, but rather how we can do it to actually solve the differential equation that appeared to be unsolvable. Okay, so this one, and I didn't make that clear, I suppose, is this equation right here, number 1, it is unfamiliar in the sense that we don't have a tool how to solving it, even though, well, hold on a second. Yeah, I mean, the only tool that we have right now, either integration, it doesn't work because we have y on the right, or in the second one, we hopefully have separation of variables, and there's no separation of variables here. Okay, so yeah, so the substitution was the only tool that's available now, and so we now have available. So a matching problem. So I saw the picture here, and then it reminds us of the picture of the heat exchange. Okay, and what is the analogy? I'm not sure entirely. The population growth versus temperature that the coffee is brought into cold room, and if it's cools down. Another one is, now that's very similar. Look at the problem at the bottom. What happens if we combine regular deposit with compounded interest? What's going to happen?
The amount added to your account every period.
Well, no, that's supposed to be your savings. So there is interest, but then you also contribute part of your salary every month or every year or whatever. What's the dynamics?
When regular deposits just make it linear, and the compound interest is just gonna raise each one significantly more over the period.
Yeah, kind of, but isn't there an easy way to get to the answer? You can argue that way, surely, yeah, if you want to guess, but we can do better than that by far. What the hell is the difference? It's still about population of people, population of money. It's the same thing. People, multiply, and then so there's money. That's what interest is. So people move in, move out. That's exactly either you're spending money or you saving money. So it's the dynamics will be exactly the same as with the population. So these two pictures will entirely apply to your bank account, depending on where deposits or withdrawals, right? Withdrawals are also possible, in which case you are on one of these pictures also will apply, in which case there will be conversions towards a constant value. Oops, if your if your interest is naturally, if it is saving, then the interest is positive, and so you are, the picture is on the right, so there is still growth, but it could decay. Okay, if you're withdrawing too much money. So your interest does not provide you enough money in order for you to withdraw, and then what's going to happen? It will go down exponentially. At some point, it hits zero, and so then that's it. So I'm not gonna read it. It's slightly developed here, that idea. Newton's law of cooling. The equation is, as you can see, is also very similar, and that's the difference between the room temperature is zero, and room temperature is not equal to zero. This is, we end up with the same exact equation that we have seen when the room temperature is zero, and it is all relative. If you think about it, who decided that the room temperature is 77 degrees or not zero? It's entirely made up. Okay, so then that the change of variables really is called right away, and the whole procedure is exactly the same, and the answer, as you can see, is entirely simple. So that has to be expected. So these are presented in an abbreviated fashion. Okay, so the simplest substitution, once again, is a shift, and they solves three problems at the same time. Population growth with influx outflux, the money with withdrawals or deposits, and the room temperature as well. We put this problem forward early on, but we only did modeling. We did not solve it because, once again, this one is look at it. It's also not solvable with the tools that we've got. So you cannot separate the variables here. I mean, you could, but well, actually, you could separate variables. I could separate variables. So I have dy over that kr. So it's actually quite possible. And then I have here dx. Okay, so it is solvable. It's not really that complicated. So that's the alternative way. Separation of variables. Okay, so when there is no y on the when there's no x on the right, then separation of variables works every time. And so if the function is simple enough, it is, then the answer once again is a fairly routine integration. So, but nonetheless, incidentally, separation of variables. Okay, so I put out these two equal to each other. I'm supposed to integrate, right? Like this. And what's the next step? If I were to integrate the one on the left, how do I do it? One word answer. What? So how do we integrate here? I would like a one word answer here. Substitution, that's right. So that substitution that we did in the context of differential equations, it's not a miracle that we came up with that idea. It comes from the same place frequently, and that's how we integrate it. So how we integrate it, if you don't recognize it among familiar integrals, then what do? You're gonna do substitution. You have 1 over z, okay, 1 over z, and then when you integrate 1 over z, that logarithm, and logarithm will produce the exponential growth or decay. Okay, so there are more examples. Try these exercises. Okay, so we're going back to discrete. So time is almost out. So let me.
I have a
Yep.
question real quick. What we were doing with the population.
Yeah.
Before, like. So we've got. Go to the original.
This over here.
Where it originally introduced the equations.
Yeah.
Okay, so if we have if our n and b are constants, right, they're not
Yeah.
changing.
Yeah.
With respect to either the population or time.
Right.
Then why can't we just integrate those in if they're constants? You know what I'm saying?
No, the integration when the differential equation that we have produced has y on the left here. On the right, I'm sorry. So when you integrate, you'll have y equal my plus b dt. Okay, so yeah, so it's a kind of circular. So best you can say it's a differential equation. It's an integral equation rather than differential equation. So it doesn't work out, unfortunately. Okay, so right. So let me just say a couple of words about where we're moving on next, and so did a little diagram here. But to summarize, this is summary what we have done here. The differential equation and what we emphasize right now for today and yesterday and then the day before is the on the right algebraic solution with separation of variables or substitution. So these are the two methods that we have so far. Okay, and saying what the alternatives and the alternatives are here. We already have covered the theoretical analysis. This is the uniqueness. And the numerical analysis we have done some of. And then there might be other possibilities. We also have qualitative analysis and maybe something else that I don't remember. But basically, this is where we would be doing. We're back to numerical analysis. Okay, so stop here and I'll see you next time. So.